Virginia. So, I hope everybody's doing well, and I am ready for joke of the day because it is the best part of the day. So, a Spanish magician tells the audience that he will disappear on the count of 3. He says, uno, dos, and then poof, he disappears without a trace. All right, but we are going to not disappear. We are going to take a look at probability and the probability of things happening. So first we need the definition of what outcomes are. Outcomes are possible results of an experiment. In other words, let's say my experiment is that I am flipping a coin. And then the possible results are that it could land on heads or it could land on tails. Let's say my experiment is that I'm rolling a dice, or a die that is. And my possible outcomes are it could land on a 1, a 2, a 3, a 4, a 5, or a 6. So anyways, that's what outcomes are, all the possible results of performing that experiment. The sample space is the entire set of outcomes. So in my example of flipping a coin, my sample space would be that it's either heads or it's tails. That's all my options. If I am rolling that die, then my sample space, the entire set of outcomes would be the 1, the 2, the 3, the 4, the 5, or the 6. An event is a subset of a sample space. So an event is kind of dependent on what is happening in the event as to how to define that sample space. We'll take a look at that a little bit more here in a minute. So let's talk about the probability of an event. So the definition of the probability of an event is the sum of the probabilities of the outcomes that make up the event. So in other words, let's take a look at this formula here. It says that the probability that an event happens is the number of times that the event does happen over top of or divided by the number of times that the experiment is performed. So let's say that I'm rolling that die and I want to know the probability that it lands on a 4. Well, I'm going to say that the number of times that it actually does land on a 4 divided by the number of times that I roll that die, that's going to be the probability that that die does the event being defined as landing on a 4. Or let's say that I'm looking at the probability that when I flip that coin that it lands on heads. So the probability that it lands on heads would be the number of times that it actually does land on heads divided by the number of times that I flip the coin. So this is that definition of probability. The number of times that the event occurs divided by the number of times that the experiment is performed. We sometimes call this relative frequency because it's relative to how often it happens. Notice that if I'm looking at this idea of probability and I'm looking at the idea of a fraction, then if it's an impossible event and there is no way that this could happen, let's say for instance that I'm rolling that die and I want the probability that it will come up as a 0. Well, there's no way that it could come up as a 0. So the probability of that would simply be a 0. It's not going to happen. On the other end of the spectrum is, let's say that, and in this situation, let's say that it's the coin and it's a weighted coin. It's weighted such that every single time it's going to come up heads. Then if every single time it comes up heads, then that is a certain event, and my probability in terms of a fraction would be 1. So it's kind of like saying this is the equivalent of 100%, and this is the equivalent of 0%. So 0% of the time it's going to happen, that's an impossible event, and we assign it a probability of 0. 100% of the time that that event will happen, we call it a certain event, and that means it has a probability of 1, because the fraction 1 over 1 is the equivalent of 100%. So you can see that your probabilities will always fall between 0 and 1. Notice that this is an equal to part on my inequality symbol, again here as well, an equal to part. So the probability is going to be greater than or equal to 0. In other words, it's okay to be 0. It's okay to be bigger than 0 because the big end of the inequality symbol goes with the big number. Small end of that inequality symbol goes with the small number. So the bigger number is that probability. It's bigger than 0, smaller than 1, but the equal to part means it's okay to be 1. So let's expand this a little bit further with this concept of probability, and then we'll take a look at some examples. So before we dig further, I want to talk about what it means to be equally likely. Now remember I talked about that die that I said it's weighted heavily so that it always lands on heads. That is a situation that is not equally likely. Because for something to be equally likely, that means the outcomes have an equal chances of occurring. So in other words, if it's a normal coin and I go to flip it, then it's just as likely that it'll land on heads as it will land on tails. Or that instance of rolling that die. It's just as likely that it'll land on a 1 as it will a 2, as it will a 3, as it will a 4, as it will a 5, as it will a 6. So that means that those events are equally likely outcomes. Everything has an equal chance of occurring. So when that's the case, then we can take that definition of probability that we had before, that we said it's the number of times that the event occurs divided by the number of times that the experiment is performed, and we can kind of expand that a little bit, and we can say it's going to be the number of successes. In other words, if this is what I want to happen, this event, the probability that the event happens will be the number of successful times that it happens divided by the total number of possible events, which is very similar to the definition we had before. This is the more common definition that it's used. That's why it has a box around it. And the other one is used a little bit, but this is the more common, the one that you see. Successes over total is how I frequently abbreviate it. Successes over total. And that is my definition or my formula for probability. But when the outcomes are not equally likely, then you have to add up those individual probabilities. This is if they are equally likely, then it's a very simple formula. So let's take a look at an example here. It says that I'm looking at an assembly line, a production line, and the production line is making digital picture frames. And so what I'm going to do is I'm going to select 3 of those digital picture frames, and I'm going to test them to determine if they are defective or non-defective. So in other words, I'm a quality control person. So if they are defective, it's going to get labeled with a D, and if it's not defective and it works just fine, then it's going to be labeled with an M. So my outcomes in the sample space are going to be represented by these strings of letters. Now remember, I'm pulling 3 digital frames. So I pull one digital frame, it's either an N or a D. I pull the next digital frame, it's either an N or a D. And I pull the last digital frame, it's either an N or a D. So my sample space is going to be represented by 3 letters, like you see right here or right here. So for instance, it might be the first one's defective, the second one's not defective, and the last one's defective. Or perhaps the first one's not defective, the next one is defective, and the last one is defective. So this is how I'm going to represent my sample space. So in my first question, I'm being asked, list all those elements that are in that sample space. So like I said before, and I'm going to be systematic about this, I pull the first digital frame. Let's say that it does come out to be defective. Well, then when I pull the next digital frame, let's say that it as well is defective, and let's say that I pull the last digital frame and it is as well defective, and all 3 of them are defective. But let's say that I pull that first digital frame and it's defective, but when I pull the next one, it's not defective. But let's say the last one still is defective. Or let's say I stick with that first digital frame being defective, and let's say the second one is defective, but let's say the last one is not defective. So what I've done here is I've exhausted all the options where the first 2 are defective, and I've got the last one being defective, the last one not being defective. So let's say that I go with that first one being defective, and now I switch that second one to being not defective, like I have here, but that last one is also not defective. So I've exhausted all options where the first one's defective, the next one is not defective, and then I've switched these up. But let's say that the first one is defective, and let's say that the second one is, I've exhausted all the options where the first one is defective. I have no other choices because I kept the first 2 defective, switched these, kept the next one not defective, and switched those. So those are all the options with the first one being defective. So let's say I pull the first one and it's not defective. But let's say I pull the next one, it is defective, and the last one's defective. But let's say I pull that first one and it's not defective. But let's say that the second one is still defective, that the last one is not defective. So here I've exhausted all options with the first one not defective, the last one defective. But let's say I pull the first one, it is defective, but not defective, but the second one is not defective as well, and the last one is defective. But let's say we keep the same idea, first one not defective, second one not defective, last one not defective. So here I've exhausted all options where the first one is considered to be not defective. Not defective, defective, switch them up. Not defective, switch them up. So here's all of my outcomes that are possible when I pull those 3 digital frames. And I have 8 elements in my sample space. Now, honestly, I should not have circled that because I was not told to count how many elements. I was told to list the elements. So truthfully, this would be my answer, listing all those elements. This is just saying how many they are, which is going to be important in the next couple of questions. So let's take a look at a situation now where we're going to take this idea and continue to run with it a little bit and see some of the things that could happen with it. So let's say that in this example, let's say we want to express the event that we have exactly 1 frame is defective. One and only 1 frame is defective, no others are. And we want to express this as a set. So in other words, what that's telling me to do is it's saying, okay, list out those elements, list the sample space for this particular event. Exactly 1 frame is defective. So we could have a situation where we've got the first frame is defective, but the next 2 are not. We could have a situation where the first frame is not defective, the middle one is, but the last one is not. Or we could have a situation where the first 2 are not defective and the last one is. Remember, it says exactly 1 frame defective, and that's all. So I have to have 2 that are not defective, 1 that is defective, and these are my 3 options for that. And so this is the event that has exactly 1 frame defective. There are 3 elements in this sample space, which will be helpful. But again, my answer was to list those elements out. Now, let's take this a step further, and let's say that my next question says, what is the probability that exactly 1 frame is defective? So now what we're doing is we're taking the information that we just gathered and we're saying, okay, based on what we just saw, that there are 3 elements that will make it happen, that we only have 1 frame defective, what is the probability that that 1 frame will be defective? Now we need to recall that definition of probability, or that formula for probability, that says the probability of an event is going to be the number of successes over the total number of outcomes. So in this case, the number of successes would be 3 right here. There were 3 ways that we could come up with 1 defective picture frame. So I have 3 successes. My total is the total sample space. When I pull out those 3 digital frames, how many different outcomes total can I have? And you recall we did that previously in that first example that says, okay, if I pull out those 3 digital frames, here's all the ways that I can make those outcomes. So I have 8 total possibilities. So that means that in my formula for probability, successes over total, then my total is going to be 8. And so this is the probability that I'm going to pull a frame, or 1 frame, and only 1 frame that's defective. So now one more example. And it says, what is the probability that more frames are defective than not defective or non-defective? Well, recall that the definition of probability says that it's going to be the number of successes over total. So probability of the event will be number of successes over total. we have to define what a success is. A success in this case is having more frames that are defective than non-defective. More defective. So if I go back and I look at that sample space that I had created back here, I want more defective than non-defective. So here's a case where I've got more defective than non-defective. Here's a case where I have more defective than non-defective. Here's a case, and that's all the cases. So there are 4 opportunities to be successful in that event. And so that means that the number of successes is going to be 4 in this probability. And recall that the total is the total number of outcomes in that sample space. I have 8 total outcomes in that sample space. So I reduce my fraction, because you always simplify a fraction if you can. That simplifies to 1/2. And so that is the probability that I'm going to have more defective frames than non-defective frames. So hopefully this helps you to understand how probability works, and remembering that creating that sample space allows you to be able to figure out the total in this formula for probability. Have a great day.